So I have here, this is a butterfly called a morpho butterfly, and I want to tell you what this butterfly, my nail polish, and soap bubbles have to do with one another. And so I'm going to talk to you about the optics of structural color. So normal colors are based on pigments, where you have some colors of light that get absorbed and some that get reflected. Some things, this particular butterfly for example, use geometry as a way to generate color. Let's start with soap bubbles. So when you're looking at a soap bubble, it sort of looks all shimmery and rainbowy, and as you let it sit there, even if you're not doing anything to it, the colors change and they go through different rainbow colors. So soap films are made out of something called surfactant. So the reason soap works is that you've got oils on your skin and you want to wash them away with water. So you have to have a molecule that has some oil favoring portion and some water favoring portion, and they have to be stuck together. So these are things that are like lipids. So in a soap film, we've got little molecules, these little head dots, they like water. These inside parts are fatty tails. And then they assemble into layers like this. And then I'm gonna end up with water up here, water in here, water down here. So it turns out that this structure is enough to get all of those interesting colors out. So let's sort of break this down. So imagine I have a bunch of layers like this, and they're some distance d apart. I'm gonna send in some wave of light. So it comes in and some of it gets reflected. So this is angle theta, and then this is also angle theta. So things get reflected by the same angle. Some of it's gonna keep on passing through, and this again is angle theta, and then it's going to bounce out at angle theta and come back out here. So now I've got two waves of light that have traveled a different distance. And for us to be able to see them, we need to make sure that they're both in the same phase. So if I had two waves of light, let's say like this, and one like this, and I want to add them together, this one I get nothing. So the peak up here cancels with the trough down here, and I got nothing. So for me to see anything, they both need to have peaks in the same place and troughs in the same place. And everything we're gonna look at is the distance between neighboring peaks, and this is the wavelength, and we're gonna call it lambda. So we wanna add these two together to get a more intense signal. Okay, so what we want to get out of this is a condition on the light so that we see a certain wavelength, and that's going to be a function of the distance and the angle. So we're going to work this out. So now let me label some points on here. Let's see, the wave travels in like this, where it intersects the first one. I'm going to call this point A. Point B is going to be the second place it intersects, and then point C is going to be the first reflected bounce. And then now I'm gonna draw a right angled line up here. So this is a right angle with this, and it's going to intersect this original beam at point D. So now what we're going to do is we want a condition that the light is gonna have traveled in here, bounced off, and goes from A to D. And then the light down here, it's going to have traveled from A to B to C, and we want to make sure that it's in phase at the same point it gets to D and at the same point it gets to C. So that's going to give us a condition, and that condition is that the distance it travels on the bottom, so that's going to be length AB plus the length BC, is going to be some multiple of n lambda plus the distance from A to D. So we're gonna do this using a little bit of trig. So I'm gonna write down the right triangle here, and then that'll be everything we need to know. So this is my right angle, and this is angle theta. It has a hypotenuse h. What I know is that this bottom leg here is going to be h times cosine theta, and the vertical line here is going to be h times sine theta. Using this triangle, we're going to work out exactly what these distances are. So our first triangle we're going to look at is A B, and then the right triangle that's down here. So I know that this vertical distance is length D. That's the distance between my layers of soap. So what I know is that the length D is equal to the length AB times sine of theta. So that's one condition. That tells us that length AB is equal to D divided by sine of theta. Okay, so now we need to figure out what the length from A to D is. And so we've got another right triangle here. So now I know that the length from A to C is the hypotenuse of this triangle. So that tells me the length AD is equal to the length AC times, in this case, this is going to be cosine of the angle. So this is cosine theta. So now let's work out what AC is. So we almost have this. We can go back to this triangle that we started with here. What we know is that half the length from A to C is the length from this intersection to B. And so we can use our right triangle again to solve this. So we know that the length AB is the hypotenuse. So half of the length from A to C is going to be AB times cosine of the angle theta. Okay, so now let's put this together. So we get AD is equal to 2AB cosine theta squared. So now we know what this distance is, and we know that AB and BC are the same distance. So this gives us a way of relating the distance D to the angle of the incoming light and the wavelength of the light. And the wavelength of the light is what gives us the color. I guess I should write out the final equation. 2D times sine theta is equal to n times lambda. So lambda is the wavelength of light, and that determines the color. D is the thickness of layers, and theta is the incoming light. The soap films are filled with water, and the water is constantly draining out of it. And so the layers are getting closer and closer and closer together. And what you're seeing is that as the layer thicknesses change, you're going through this whole rainbow spectrum of colors. So why don't we see this in everything? To make these layers this kind of size, it's pretty special. So wavelengths of light are in the hundreds of nanometers. The periodicity in a crystal is in 0.1 nanometers. That's 1,000 times different from each other. So how is biology going to get something with a really regular patterning like this? And it turns out that what biology does is it turns to these things called minimal surfaces. So this is the ideal shape of a soap film if you stretch it across some boundary. So this is something that's really easy for nature to make because cell membranes are basically just fancy soap films. So it can use this idea to pattern structures that are a specific wavelength. And it turns out that the structure that's used in the morpho butterfly that's sitting right here is something that's called a gyroid. And I've got a model of a gyroid in my bag to show you. Let's see. It's got yarn stuck to it. So this is a 3D printed model of a gyroid. So this is really intricate surface. But it's really something that's quite easy to make just from soap membranes. And this is the structure. It can set the periodicity of the layers here to the right kind of blue that you're seeing in that butterfly.
So what's the butterfly making gyroids out of? Because it hasn't got soap in it.
If you zoom in really far on a butterfly wing, you get wing scales, these little pillars that have shapes in them. And if you zoom inside those, each one of those was once a cell. So it had a living cell membrane. So the cell membrane takes this shape and then it infills half of it with a protein called chitin. And then after the cell dies, the cell membrane gets stripped away, but what you're left with is a protein that has this templated into it. And that's what's giving it this color. It's really this complicated, beautiful surface that's giving this really striking blue to this butterfly.
So if you were to do that diagram again for the butterfly, all the numbers would work out to give us the wavelength of blue light.
Yeah. And so one thing that you might notice is that in the soap film, you really saw a lot of rainbows. In this, it's pretty similar color when I tilt it around. So you'll notice that it gets a little bit more or less intense, but the color itself doesn't change. And that's something we didn't see with the soap film. So the soap film, the angle really matters. And so something about using this kind of structure is it has repeated angular structure, but when you come in at different angles, it behaves a little bit like it's all layers in all the same direction.
And what's happening with your nail polish?
Yeah, so my nail polish is something that's called a diffraction grating. So it's not quite the same thing. It turns out it's polypropylene. It's a polymer that's doing all of this, but it's effectively a film that has a bunch of repeated layers in it. And instead of it being layers this way, there are layers this way, and that's reflecting light off differently in different angles, and it's exactly the same optics that's going on.
Were you impressed that I had one of those butterflies ready for you?
Absolutely. That was fantastic.
Yeah, we didn't even plan that. I just had that on the wall.
Yeah, and it's exactly the right butterfly. It's a beautiful butterfly.
Just think, when that butterfly came to its unexpected demise, it didn't know it was going to be in a Numberphile video.
Yeah. Well, now it's famous.
Doesn't do it much good though, does it?
No. Poor butterfly. It's beautiful.
What this man doesn't know about moths and butterflies isn't worth knowing. And the collection they have here is extraordinary. We couldn't possibly look at them all, but let's look at some.